Hi everyone, I'm Ifan from Group 12, and today with my teammate Choi Chuan and also Xiao Mingxuan, we'll be presenting our project, which is a DIY firefighting robot using Arduino, and it's an auto flame chaser with alert system. So firstly, we will be discussing about our design specification. So basically, our robot is designed to detect and respond to fire. We use 3 IR flame sensor to identify the direction of the flame, and we use 2 BO motors for movement by using L298N motor driver. We triggers a buzzer as an audible alert when flame is detected, and for our further enhancement, we can integrate water pump and servo motor to extinguish the flame. Next, for other specification, we use hardware such as Arduino Uno as our main microcontroller for processing and control, and also use 4 3.7 battery as our main power supply for the system. In terms of the features, the flame detection helps us to trigger robot movement towards fire, and the central sensor ensures precise targeting. So for further enhancement also, we can use the submersible water pump for spraying water to extinguish the flame, and also water tank for water storage purpose. And in terms of features for the further enhancement, pump activation can work when fire in range, and servo motor help us to adjust spray direction dynamically. So now we are moving to the system modeling part. Basically, our motor is a second order transfer function where we have the angular position divided by the input voltage to motor, and the J will be the moment of inertia of the motor and load, B will be the damping coefficient, and K will be our motor constant.
So for system modeling and for our current implementation, when flame is detected and the flame sensor is triggered and send signals to Arduino Uno will process the signal and send to the motor driver. And later motor driver will determine the desired distance and position to the flame, and the buzzer will kick active before the flame pull up. So for our future enhancement, since we use the water pump and later water pump will spray the water together with the servo motor.
So next, we'll be moving to our electrical and mechanical system. So for the left one will be our circuit diagram, which consists of all the circuit connection of our system. And next, we'll be moving to the block diagram, where the power supply will be linked to the flame sensor module. And after the flame sensor is activated, it will send signal to the motor driver, and the motor driver will send the signal to Arduino for processing purpose. Next, the Arduino will send command to the servo motor and also DC motor for the movement of the robot.
Hi, my name is Ming Xuan, and today I will explaining the main sensor used in our robot, which is flame sensor. So this sensor is used to detect the presence of the fire by capturing infrared light, specifically in the 760 to 1100 nanometer range. It has a detection angle of 60 degree and can detect the fire up to 80 centimeter away, depending on the condition like flame size and lighting. We use three sensors, left, center, and right, to help the robot to locate the fire direction more accurately. So mathematically, its analog outputs follow an inverse square relationship, which is the closer the flame, the higher the output voltage, based on the formula V out equal to K over D squared. This is used by the Arduino to determine how close the flame is and where it is located. Okay, now I move on to the transducer in our robot, which is buzzer. So it acts as a role to alert us when a flame is detected. Once the flame sensor pick up a signal, the Arduino will trigger the buzzer. So the buzzer normally operates on 3 to 5 volts and draw about 30 milliamps and making it power efficient. So the buzzer follow a very simple binary on or off behavior represented mathematically as when S is equal to 1, the flame is detected, the buzzer will on, and when S is equal to 0, the buzzer will turn off. So in order to move our robot, we plan to use two BO motor and place it on each side of our robot. This motor will help us to convert electrical energy into the rotational motion to drive the wheels. Each motor normally operates between 3 to 6 volts and run about 150 to 300 RPM with enough torque to move the robot and carry extra components. The motor are controlled by using PWM signals through an L298N motor driver connected to Arduino. The motor's behaviors is described by several equations, which is electrical equation, mechanical and torque-related equation, and finally combined into a transfer function as shown in the slide. And this transfer function shows that how the voltage input controls the angular speed. Although we don't apply a full control model here, but this theoretically understanding will help us for the future upgrades of PID control. Okay, now I move on to the optional transducer that we may make a future enhancement on our robot. Currently, our robot is used to detect the fire and give an alert. In the future, we plan to enhance it with a water pump and a servo motor for fire extinguishing. The submersible water pump we plan to use normally operates from 3.3 to 6 watts and provide a flow rate of 120 liters per hour. It will be triggered automatically when fire is detected, and the servo motor will rotate the nozzle to aim the water and spray it accurately. So for the mathematical model for the pump is very simple, which is Q equal to K times V minus V. And this equation shows that the flow rates increase with voltage. This model helps us to estimate the water delivery based on the power supply. So move on to the electronic hardware that we use is Arduino Uno. So we can see that all the components are integrated using the Arduino Uno, which act as the most important part and as a brain of our robot. As we can see from the pin connection table, the analog pins A0 to A2 are connected to the flame sensor, while the digital pins D5 to D10s are control the motors through the motor driver. And lastly, the buzzer is connected to the analog pin A5. This setup allowed the robot to receive the flame signal and process them to move in the correct direction. And lastly, the buzzer helps us to alert when a flame is detected. So besides that, the Arduino Uno is ideal for this project because it is very easy to program and help us to support many inputs or output pins and has a very strong community support.
Hi, my name is Choi Chuan. In this video, I want to present the PID controller, SolidWorks, and the expected result and output. So we apply the PID in our firefighting robot. The goal of PID in our design is use the three flame sensors to determine where the flame is, and we calculate an error to determine how far the flame is from the center based on the left and right sensor readings. And we use PID control to adjust the motor speeds so the robot turns smoothly and directly towards the flame. For the application on our design by PID control, we use three inputs: the left, front, and right flame sensors, and all read all reading take the analog values. So to determine the error, we use the formula error equals to left reading from the left sensor and the reading from the right sensor. If error greater than zero, the flame is more to the left, so the robot turn left. And if the error is smaller than zero, the flame is more to the right, so the robot will turn right. And if the error goes zero, the flame is centered, no need to turn. So for the PID output, the PID adjusts left and right motor speeds based on PID output, and the output is a value added or subtracted based on from base motor speed. So the next is how we tune the PID manually. First, we start with adjusting KP equals to 0.5, KI equals to 0, and the KD equals to 0.2. If the robot is overshoot or oscillate, we will decrease KP to make the robot respond slower and smoother, or we increase the KD to slow down and move gently near the flame. If the robot reacts too slowly, we will increase KP to make the robot respond faster, and if it drifts slowly, we will consider increase KI. So for the summary, PID logic reads flame direction using sensors, calculate directional error, and adjust motor speeds for smooth turning, and move robot toward the flame and stop with center, and the robot and the flame comes to the desired distance. So this is our first design on SolidWorks before the real one. First, we design a base as the car chassis, and we insert the Arduino Uno to read the analog value of three flame sensor, front, left, and right, and give the output to L298N motor driver to control the two BO motors for movement toward the flame, and we insert the buzzer to activate as an alert. Lastly, we design the battery case to act as the power supply of the motor. For the expected result on our design in current implementation, we expect our robot can detect flame using three flame sensors, determine flame direction using analog sensor values, and when the sensor detects the flame, the buzzer will activate, and the robot move forward or turn based on flame position. And when fire is detected in center position and fixed distance we set, the robot stops and buzzer keep activate as an alert until the flame extinguish. Lastly, the robot stop if no flame is detected. For the future enhancement result, we expect the robot will stop once flame is strong and centered. Rotate servo motor to aim the nozzle toward flame direction. Activate water pump using TIP 122 transistor circuit. Spray water through a pipe to extinguish the fire. And sweep the spray pattern with servo left to right and center. And turn off the water pump after sweep is completed. For the expected result, we use the PID controller on our design. By applying the PID coding in Arduino, there is the output, a part of output that we take from the serial monitor in the Arduino IDE. So from the output, the flame LFR is the analog values from the flame sensors on the left, front, and right flame sensors. The lower the values indicate strong fire detection. For example, we take a row as the right flame sensor show the 290 means that the fire is strongest on the right. To calculate the error, we use the formula that you use the analog value left flame sensor and minus the analog value right flame sensors, which is 435 minus 290 equals to 145. A positive error means the flame is on the right. So for the output PID proportional term, Kp times error equals to 0.5 times 145 equals to 72.5. This value controls how much to adjust the motor speed. The L speed or the arrow speed is the motor speed commands, which is the left motor and the right motor. For the left motor, 160 base reading plus 72.5 equals to 232, and the right motor 160 minus 72.5 equal to 87. This makes the robot to turn right smoothly toward the flame.